Hi everyone, welcome back. In this video, we are going to start a very important topic of the EM waves, which is EM waves in a conductor. Basically, in the previous videos, what we did EM waves in vacuum, then we did EM waves in dielectrics, and now it's time to move on to this topic of EM waves in a conductor. I'll try to cover this topic into 2-3 videos. So this would be the part A, or this would be the part 1. So basically what we are going to cover in these 2-3 short videos, first would be the assumptions, key assumptions that we take. And these assumptions are actually very important. If we understand the assumptions, then we are going to understand the whole topic, hopefully. Now, and after assumptions, we'll try to write the Maxwell's equations for the EM wave in case of a conductor. And basically, we have two types of the Maxwell's equations here. And you don't need to get confused. I'll try to make it very easy for you, and it's actually very easy topic. Then we'll write the wave equation, how the wave equation is different from that of the EM waves in case of the free space and in case of the dielectrics. So basically we'll do a comparison, but there would be a whole detailed comparison in the third part of the videos, in the third part of the video. So we'll also discuss a certain concept of secant depth, and probably will also understand attenuation and the phase shift. Then final we will understand the comparison. So let's go directly with the assumptions. The first assumption, since we are sending the electromagnetic wave into a material, so the first thing, the material should be a conductor. I'll try to make it a bit clear because I'll use it for the whole video, this diagram. So the material, this material should be a conductor. So first thing is material is conducting. So what we mean is that it has finite conductivity. Finite conductivity, sigma. Because finally what we would be sending an electromagnetic wave into the material, and this should be a conductor. It must have some finite conductivity. And second assumption is connected to the first. That means it should follow the Ohm's law. Ohm's law should follow. That is JF equals sigma E. Now here I introduced JF. Now I'll make you understand what I mean. So basically there initially when we have the conductor, and we don't initially send the electromagnetic wave, so basically rho f is not equal to 0 and JF is not equal to 0. So neither the rho f, which is it's free volume charge, is not equal to 0, and JF is its free current density. It is also not equal to 0. But when we send the electromagnetic wave into the material, then this JF becomes 0. That would be the second case. And for this case, when JF is not equal to 0, we write the Maxwell's equation for this. And when we send the electromagnetic wave, then because of the electric field interaction with the charges, but we know inside the conductor electric field should not exist. So basically this rho f, this free charge density vanishes, and it becomes 0 actually. So basically it becomes later on 0. So we'll have two types of the Maxwell's equation for this. Okay, and this free current density JF should follow the Ohm's law. That's very important thing. Okay, I'll come to this this thing and this thing in a bit. But for right now, what you have to understand that this free current density follows the Ohm's law. That's very. important. And one more thing, the charges present inside the conductor that are natural conducting electrons. So we have natural conducting, or natural conduction electrons rather. So we don't place actually external charges into the material. Whatever the charges we have here, those are all intrinsic, or we should say the natural conduction electrons which the conductor have. So and then these conduction electrons, these conduction electrons react to the electromagnetic wave, or they rather react, so finally react they react to EM wave, or electric field of EM wave, and they respond to that, or they reacted dynamically to the oscillating electric field. But one more thing, I'll try to remind you that these charges are not the charges that we put from outside, but rather these are natural conduction electrons inside the conductor. I hope you understand these three assumptions. So material is conductor, there is no problem that it is a finite this conductivity, and this pre-current density should follow the Ohm's law, that is Gf is equal to sigma E, and these are the natural electrons, or the natural conduction electrons inside the conductor, and they react to the electromagnetic wave. This electromagnetic wave, they react to it dynamically to the oscillating electric field, because the electromagnetic wave will have electric field, magnetic field in it. Okay, it has electric field and the magnetic field in it. So electric field would be oscillating, and those electrons will react to that. Now let's come to the very important concept, that is, second thing is Maxwell's equations. So basically we have two types of the Maxwell's equations here. One we will write for this situation, and I'll also explain it a bit. Let me put it here. Okay, this, and I'll write Maxwell's equation for this as well. Let me put it here. I hope you are able to see it. Now see, initially, because this is the conductor, so both rho f is not equal to 0 and jf is not equal to 0, and that is important property of the conductor. And when we send the electromagnetic wave into it, so basically it takes time. If there is some momentarily accumulation of the charges. So here there is some momentarily accumulation. So there is momentarily accumulation of charges inside the conductor. Let's say here is a momentum, but that is momentarily. Okay, that's very important for the very short period of the time. So that leads to the rho f is not equal to 0. Okay, and this is actually more, it is actually a general, we call it a general or transient situation. So it does not last for so long. It vanishes after some time. So that's why we call it as a transient. So it's in the transient state. Okay, this is not fixed. Rho f is not equal to 0. This situation doesn't go for so long, but it is there for very few moments. Okay, that's why we call it as a momentarily accumulation, and after that time it vanishes, and it goes to this case where rho f is equal to 0. So this case is actually used for steady state, and we're interested into this case, because after some time the rho becomes 0 inside, and all the charges will accumulate to the surface. This is the very important property of the conductor, that all the charges will come to the surface. Okay, used for the steady state or high frequency electromagnetic waves. where no charges builds up, where no charges builds up. If you understand these two things, then we can go to the now Maxwell's equations. Okay, only third would change, only fourth would change. There is no problem. I should erase it. Okay, so these two cases, one, rho f is not equal to 0. It's a more general transient situation where charges can momentarily accumulate, and second is that rho equals 0, which means that it's used for the steady state or the high frequency electromagnetic waves. Okay, so I think now it's time to move to this case. Let's write the Maxwell's equations. We know del dot of E equals 0. Del dot of E is equal to, rho by epsilon 0. Del dot of E would be here 0. Del dot of E equals 0 here, because rho f equal to 0, but here it would be rho f by epsilon. Okay, one more thing, there wouldn't be epsilon 0, but rather it would be epsilon, because it would be the permittivity of the conductor. This will be the first Maxwell's equation. Here it would be first Maxwell equation here. Let me put it a bit down for the comparison purposes. Okay, now second del dot of B equals 0. There is no problem in that. Del dot of B equals 0. Third, also del cross of E equals minus dou B by dou T. Third, del cross of E equals minus dou B by dou T. Now, fourth equation says that del cross of B is mu 0 J, but here we have mu because it's a conductor, so we write it's permeability of that material, and it is JF rather than whole J, and plus mu 0 epsilon 0, but we have here mu and epsilon dou E by dou T. This is important. Now we'll use here Ohm's law, because JF will follow the Ohm's law. That's the basic assumption here. So in place of JF, we'll write as the sigma E. Del cross of B is mu sigma E plus mu epsilon dou E by dou T. There is no problem in that. So similarly, we'll write here del cross of B equals mu sigma E plus mu epsilon dou E by dou T. So basically, if you see, there is only one change that is into this equation. That's the Maxwell's first equation, which is actually the Gauss law. So there is only a bit variation into that because of this case, rho f is not equal to 0 and rho f is equal to 0. But this is actually important for us. This is important for us because finally, when electromagnetic wave interacts with the charges inside, so any local charge imbalance, if there is some local charge imbalance here, so they rearranges very quickly. That rearranges very quickly, and when electric field is applied to that. So when while during the rearrangement, so any local imbalance, so this local imbalance will almost disappear. So this local imbalance would disappear finally because of the electric field present in the electromagnetic wave. So finally, rho equals 0. This is the important case for us, because after that time we'll try to evaluate that time as well. Okay, we'll try to evaluate that time as well, and that time is actually the characteristic time of the material. This is one of the important concept, and we'll try to cover that concept in this video as well. Okay, so now how the important thing, third important thing is how charge decays on surface of conductor. I told you if there is some local imbalance because of the electromagnetic wave or because of the electric field present in the electromagnetic wave, then it disappears almost instantly. almost instantly to the surface. Okay, now let's see how. We know the equation of continuity. Del dot of J equals minus dou rho by dou t. I hope you know this. I don't need to derive it right now. I'm not interested into that. And since we have here free current density and the free charge density, so it is JF and rho f. It's very important. Okay, now what we do is that in place of the JF, because the assumption is that these free current density would follow the Ohm's law. So in place of JF, I'll write del dot of sigma E equals minus dou by dou t of rho f. Okay, now let me take this sigma outside. So there is del dot of E equals minus dou by dou t of rho f. Okay, now see, what I'll do is in place of the del dot of E, I'll write rho by using this equation, rho f by epsilon. Okay, so I write sigma into rho f by epsilon equals minus dou by dou t of rho f. Okay, so now we have here rho f and we have here rho f. So I'll try to separate the variables. Okay, I'll write it in this way, tau rho f by rho f. Sorry, let me write on this page, dou rho f by rho f. Okay, equals minus sigma by E dou t. Okay, I took this dou t to the left side and this rho f here. Okay, so because I trying to separate the variables. Now we don't have any option rather than the integration, so I'll integrate it. So which implies it's ln of rho f equals minus sigma by epsilon, and it's t plus some constant. Okay, ln of some constant, ln of rho f0. Now I'll tell you why I wrote the rho f0 here. Okay, it's very important actually. So initially when t equals 0, initially t equals 0, rho f would be equal to rho f0, because there would be some free charge density in a conductor. Okay, we can do it in a different way. We can do it like, I can take it as constant. Okay, then put here t equals 0. Let me take it as c. So basically we'll find this constant. Let's consider this as a c. So at t equals 0, initially there would be some rho initial free charge density. It would be different than what would be at any time. So I'll consider that at t equals 0, it is rho f0. So what this equation would become, ln of rho f0 equals this constant c. Okay, so then we put here back, so it would become this. Otherwise you can write here as c. There is no problem in that, writing here some integration constant, which is c. Okay, so let's put it now back. So it's ln of rho f equals minus sigma by epsilon t plus ln of rho f0. Okay, so now let's take we need to find this rho ft. It is actually the function of time, because it's not constant, it varies. So initially at t equals 0, it is rho f0, and at any time it is rho ft. We'll see, and it should decrease actually. I told you initially it has some value, so there are some charge imbalances in a conductor, but when the electromagnetic wave enters into it, or when electric field interacts with the charge density or the charge imbalance, so it decreases, it decreases and it comes to the surface. So basically we are interested into finding the rho of t. Okay, let me take this left side, ln of rho ft minus ln of rho f0 equals minus sigma by epsilon t is basic mathematics. There is no hi-fi mathematics here. Ln of rho ft by rho f0 equals minus sigma by epsilon t which implies rho f t equals rho f0 e to the power minus sigma by epsilon t. Is that equation correct? Yes. So this equation is very important equation. This equation is very important equation. What it says, now check yourself, it says that initially when t equals 0, so its value is rho f0, but as time increases, I can write it in a very different way, not so much different, but rho ft equals rho f0 divided by e to the power sigma by epsilon, sigma by epsilon t. See, initially at t equals 0, this is e to the power 0, which is 1, so initially it has a value of rho f0, but as time increases, this whole value increases and it gets divided to the rho f0, so this rho f t decreases. So if we try to plot it, so initially at t equals 0, its value is rho f0, and as time increases, and as this is at t equals 0, and as time increases, its value decreases. Okay, so it is rho ft, directly proportional to the e to the power minus sigma by epsilon t. Okay, it's very simple. So this is very important, that when electric field interacts with the this charge imbalances, which is like rho f inside the conductor, then it starts decreasing and it comes to the surface as time goes on. So now there is important time which we called as the characteristic time. What is characteristic time? It says that after what time rho ft becomes rho f0 by e, where e is 2.71, we know that. Okay, so that is it is value becomes rho f0 by e. As I told you that rho ft decreases, it's rho f0 value here, and this is rho ft, so it goes on, so it decreases. What is the time? Let's say after this time t equals tau, its value becomes rho f0 by e. Okay, so what's that time? How much is that time? So we need to simply put this equation in place of the rho ft. We have rho f0 by e equals rho f0 e to the power minus sigma by epsilon. Let that time be tau. After this time t equals tau, rho ft becomes rho f0, what was initial value, divided by e. So this will go on with this thing. So it would be e to the power minus 1 equals e to the power minus sigma by epsilon tau. So which implies sigma by epsilon tau equals 1, which implies tau equals sigma epsilon by sigma. This is one of the very important equation in this topic. Tau is epsilon by sigma, where epsilon is epsilon 0 epsilon r, so which implies tau is equal to epsilon 0 epsilon r by sigma. Okay, this is very important. Now you need to remember here two things. One is good conductor, and we know that good conductor is that having a very high conductivity. Sigma, I should say sigma is very high. And or I should say infinite. And it also means that this characteristic time tau tends to 0. We want that the conductor should actually move this charge imbalance to the surface as fast as it could. So this tau characteristic time should be 0. If characteristic time is 0, we say it's a very good conductor. So we say it's an ideal conductor or a good conductor. It means the charges will decay very fast to the surface. These charges will decay very fast to surface. We want it to do it very fast. Okay, we want no time to take it to move all the charges, free charges, to the surface. If that happens, then that is a good conductor. Actually, that's an ideal conductor. So what is poor conductor? Poor conductor is obviously sigma tends to 0. It's very low, conductivity is very low, or this characteristic time is infinite, that it takes a infinite time. It takes a very large amount of the time to move this this free charges, or this charge imbalance, or the momentarily charge imbalance in a conductor to the surface as fast as it should take very large time to do that. So it will not decay to surface. It stays inside. It stays inside. Okay, and because of this, hence material polarizes. Actually, material polarizes. I'm not going into the details of this thing, but yes, here I would stop. I'll move to the EM wave equation in the next part of this video. Thank you so much.